Hi guys, in this video we are going to perform a multiple linear regression using a data set called the cement-data.csv that contains the data for the amount of feed generated in a cement mixture using different combinations of four different combinations of the percentages of four different ingredients. So let's start by loading our data set. So we're going to load our data set. We're going to name our data set as cement data, and it's going to be a read CSV file. So we're going to use the function read.csv, and our data set is named at cement data.csv, and we're going to do header. Header is going to be true. Let's run that. Okay, okay, I made a mistake there. So let's run that again. So as you can see, our cement dataset has been loaded. Let's have a look at the dataset. So we're going to explore the dataset. So we're going to do str cement data. We run that. As you can see, our str function gives us output, and it tells us that the data frame cement data, it's a data frame that contains 13 observations of 5 different variables. So as you can see, there is the ingredients list. So ingredient 1, ingredient 2, ingredient 3, ingredient 4. And these columns contain the percentage of ingredient 1 used in making the cement mixture and the heat produced by that combination. So for example, in the first row, we can see that 7% of ingredient 1, 26% of ingredient 2, 6% of ingredient 3, and 60% of ingredient 4 were used to make the mixture, and the heat generated by this combination of ingredients is 78.5. Okay, so that's our data set. So now let's try and do multiple linear regression on this model. So multiple linear regression with heat as the response variable, and the rest as the explanatory variables. Okay, so first we're going to separate the response and the explanatory variables. Now the way we do that is we're going to do y is going to be cement data dollar heat, and x is going to be cbind. We'll have to convert this into a matrix. So cbind as matrix, cbind. We're going to replicate 1 13 times, and we're going to bind this with the cement data, the first four columns. Okay, so that's our y and x. Now we're going to calculate the intercept um, and the coefficient of our multiple linear regression model. So we are going to calculate the intercept and other coefficients using the formula. So the formula is going to be beta is equal to the transpose of x. So I'm just going to write it out. Transpose of x times x, and we take the inverse of that times the transpose of x again times our y. Okay, so we're going to get beta, and the way we get the inverse is we do solve. Solve gives us the inverse, and t gives us the transpose, and we do matrix multiplication there. Okay, percent times percent t of x percent times percent of y. That gives our beta. It's gonna be a mistake in spelling there. So let's run that and see what our beta looks like. So x is not found, we didn't run it, so let's run it again. Okay, should be good. And it gives our beta. That is not what I was looking for. Let's see what mistake did you make. This thing, and this is where it should be. If we do that, there you go. This gives our coefficient, intercept, and coefficients. Now, using this, we can say that our model looks something like this. So heat is going to be equal to 62.41. That's our intercept, plus 1.55 times ingredient 1 plus 0.51 times ingredient 2 plus 0.10 times ingredient 3, and the last one is a minus 0.14 times ingredient 4. So that's what our model looks like. So we already made a model. Now let's try and see how good our model is. So we're going to check how well the model fit the data set. Okay, and the way we do it is we're going to perform kind of like a residual analysis there. So we're going to calculate the fitted y values first, and we'll name it y underscore fitted, and that is just going to be x matrix multiplied by beta of the first column. That gives our y fitted values. Now let's calculate the residuals. So we're going to calculate the residual. So we're going to residual, and that's just y minus y underscore fit. If we run that, we get a residual there. Now let's try and plot the residual to see what's going on. Plot residuals. We're going to plot our residual. We're going to give the CX of 0.8, and the line width is going to be 5, and we're going to add a line to it. A equals to 0, and B is also going to be equal to 0. We're going to give it a color. Color is going to be red, and line width is going to be 5 again. Okay, let's run that. So from the residual plot, you can see that the residuals are randomly scattered. This means that there is no pattern in the residual plot. So that means that our model is a good fit to our data set. Now let's try and quantify how good our model is, or how well our model fits our data set. So we're going to calculate the coefficient of determination. The way you calculate the coefficient of determination is we're going to do RSQ. It's going to name it RSQ, and so that's the formula. So 1 minus sum of our residuals squared divided by the sum of y minus mean of y, but we have to square it, so let's put another bracket there. So that's going to be a square there. Let's run that. So as you can see that our r squared value is 0.982723756. So that means that 98% of the variation in heat is described by our model. So our model seems like a very good fit to our data set. That's it for this video. Thank you for watching the video, and if you like my video, please like and subscribe, and I'll see you guys next time.